Our observable universe can be defined as a spherical region of space from which light has had time to reach us during the 14 billion years since the Big Bang. It is the part of our physical reality that contains everything that exists, which we can in principle observe. But is there anything that lies beyond our observable region or our Hubble volume? Well, given that our universe may be infinite in size with an intrinsic property known as inflation, chances for the existence of the multiverse are extremely high. So for physicists like Max Tegmark of MIT, the question is not whether the multiverse exists, but rather how many levels it has. He has classified as many as 4 distinct types of multiverses in his book, Our Mathematical Universe. So let's take a brief look at what these different levels of the multiverse are like. The first and the least controversial level of our multiverse is simply a region of space that is too far away for us to have observed yet. The furthest we can observe in any direction is currently about 46 billion light years, which is the distance that light has been able to travel since the beginning of the Big Bang. But just because we can't see something doesn't necessarily mean that it doesn't exist. In fact, the cosmic microwave background radiation allows us to perform extremely sensitive tests for whether our universe is finite, and so far, all the evidence seems to be against it. Now, since the flat, infinite models fit the observed data, it is reasonable to assume that our universe is infinite, or at least sufficiently large, which makes the level 1 multiverse a trivial consequence of these tests and the cosmological theory of inflation. Furthermore, observations of our galaxy distribution and the microwave background radiation have shown that the arrangement of matter on large scales collapses to dull uniformity with no coherent structures larger than about a billion light years. If this is true, then there is no reason to believe that our part of the cosmic horizon is the only one with physical stuff or matter in it. So with an infinite amount of space and matter available, a level 1 multiverse contains an infinite number of regions similar to our own observable universe. This means that there may be an identical copy of you somewhere out there in the multiverse as we speak. And not just one identical copy, but infinitely many identical copies of you may exist, as there may be an infinite number of Hubble volumes identical to our own in the level 1 multiverse. In fact, Max Tegmark estimates that if you traveled in a straight line for about 10 to the 10 to the 119 meters, you would come across an identical copy of our entire observable universe. But if you wanted to meet an identical copy of you, then the distance to that would be relatively less, about 10 to the 10 to the 29 meters away, which is still astronomically huge. So we can think of observers living in level 1 parallel universes as experiencing the same effective laws of physics, but with different possible histories. Now, if you think that the level 1 multiverse may be all there is, you're in for a surprise. Imagine an infinite set of these distinct level 1 multiverses, some perhaps with different space-time dimensionality and different physical constants. Only then you would have a structure that would constitute a level 2 multiverse as predicted by the current popular theory of chaotic eternal inflation. Andre Lind, Alex Wellenkin, Alan Guth, and their colleagues have shown that space as a whole is stretching and will continue to do so forever, but some regions of space stop stretching and form distinct bubbles, like gas pockets in a loaf of rising bread. These distinct bubbles are level 1 multiverses that are infinite in size, occurring infinitely many times, filled with the same energy field that drove inflation. But these bubbles are infinitely far from each other, meaning that if you live in one of these level 1 multiverses, it would be impossible for you to visit a neighboring level 1 multiverse, since inflation will keep creating space between your bubble and its neighbors faster than you can travel through it. So your descendants will never see their identical copies elsewhere in the level 2 multiverse. In comparison, you can in principle travel to any arbitrarily distant part of our level 1 multiverse if you're patient enough and the cosmic expansion decelerates. Now, the level 2 multiverse is far more diverse than the level 1 multiverse. The bubbles vary not only in their initial conditions, but also in seemingly unchanging aspects of nature. Meaning they must obey the same fundamental laws of physics, governed by the same mathematical equations, but may have different effective laws of physics or particular solutions to those mathematical equations in different bubbles. Now, so far, we have looked at structures that we can point to in space, at least in theory. But the next level of the multiverse, the level 3 multiverse, gets super weird. It is believed that the level 3 multiverse is right here all around us, arising from the famous and controversial many worlds interpretation of quantum mechanics. It is the idea that random quantum processes cause the universe to branch into multiple copies, one for each possible outcome. In the early 20th century, the theory of quantum mechanics described the states of our universe not in the classical terms, such as the positions and velocities of all particles, but in terms of a mathematical object called a wave function. According to the Schrödinger equation, the state of a wave function evolves over time in a way that mathematicians call it unitary, meaning that the wave function rotates in an abstract, infinite-dimensional space called Hilbert space before evolving in a deterministic way. So to explain away all the weirdness of a wave function with its many different possibilities, physicists in the 1920s postulated that the wave function must collapse into a definite state once an observation is made. However, Hugh Everett showed that the collapse postulate is unnecessary and that all possible outcomes are equally as real as the one that the observer is observing. In other words, superposition of all the classical worlds is the level 3 multiverse. So these universes are located not in ordinary space, but in an abstract realm of all possible states. Every conceivable way that the world could be within the scope of quantum mechanics corresponds to a different universe. But given infinite possibilities even at the level 1 and level 2 multiverse, the level 3 multiverse adds nothing new. It just adds an infinite number of indistinguishable copies of the same universes to the already infinite level 1 and level 2 multiverse. Well, if a level 3 multiverse adds nothing new to the previous levels, then surely there can be nothing else beyond it, right? Not according to Max Tegmark. He argues that our physical reality isn't just described by mathematics, but it ultimately is mathematics. So just like the initial conditions and physical constants in the level 1, level 2, and level 3 multiverses can vary, the very fundamental laws that govern nature itself can vary in the level 4 multiverse. In other words, a universe at this level may exist that obeys the laws of classical physics, but without any quantum effects. Or a universe that is just an empty dodecahedron. Or better yet, a universe with discrete time intervals instead of continuous. All these alternate realities actually exist in a level 4 multiverse. An indication that such a multiverse may not be just mere speculation is the tight correspondence between the worlds of abstract reasoning and observed reality. Equations, and more generally, mathematical structures such as numbers, vectors, and geometric objects describe the world with remarkable accuracy and precision. In his 1960 article, The Unreasonable Effectiveness of Mathematics in the Natural Sciences, physicist Eugene Wigner argues that a physical theory's mathematical structure often points the way to further advances in that theory, and even to empirical predictions. Moreover, according to Tegmark, mathematical structures have an eerily real feel to them. They satisfy a central criterion of objective existence, meaning they are the same no matter who studies them. For example, a theorem is true regardless of whether it is proved by a human, a computer, or any other intelligent life form for that matter. So intelligent alien civilizations would find the exact same mathematical structures as we have found here on Earth. Appropriately then, mathematicians commonly say that they discover mathematical structures rather than invent them. So for Tegmark, all mathematical structures are physically real, immutable entities existing outside of space and time. Every mathematical structure corresponds to a parallel universe constituting a level 4 multiverse. This ultimate level of the multiverse opens up the full realm of possibilities. Here, Universes can differ not just in location, cosmological properties, or quantum states, but also in the laws of physics. Existing outside of space and time, they are almost impossible to visualize. The best we can do is to think of them abstractly as static sculptures that represent the mathematical structure of the physical laws that govern them. And these are the 4 distinct levels of the multiverse defined by Max Tegmark and others. If you enjoyed it, give it a thumbs up, share with everyone you know, and subscribe to our channel for more content like this. Also, if you want to see a more in-depth analysis of these levels, let us know down below in the comments section. Until then, we'll see you in the next one.